I thank all of you for watching my videos and encouraging me. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Thank you. We now discuss the solution of a problem from the question paper CSIR National Eligibility Test held in the month of December 2023. The given question is from the section Real Analysis and it is related to an application of Weierstrass Approximation Theorem. This question is placed in part C, which is a multiple select question. There can be more than one answer and it carries 4.75 marks. The question ID is 704070. Right. The given question is, suppose that f be a function from the closed and bounded interval -1 to +1 into R is continuous. So it's a real valued continuous function defined on the closed and bounded interval -1 to +1. Which of the following imply that f is identically 0 on the interval, closed interval -1 to +1? We are given four options. Option 1, integral -1 to +1 f of x to the power of n dx is equal to 0 for all n greater than or equal to 0. If this is so, will it imply that fx is identically 0 on -1 to +1? So also option 2, integral -1 to +1 f of x into p of x dx is equal to 0 for all real polynomials p of x. Will it imply that f is identically 0 on the closed interval -1 to +1? Like that, option 3 and option 4. Option 3, integral -1 to +1 f of x into x to the power of n dx is equal to 0 for all n greater than or equal to 0 odd. Option 4, integral -1 to +1 f of x to the power of n dx is equal to 0 for all n greater than or equal to 0 even. Right. Let's now discuss the solution of the problem in detail. We have a function defined on a real valued function defined on the closed and bounded interval -1 to +1, and it is given f is a continuous function. Agreed. So let's take the option 1, integral -1 to +1 f of x to the power of n dx is equal to 0 for all n greater than or equal to 0. Will it imply fx is equal to 0 for all x belongs to -1 to +1? Right. So we recall a result. The result is, if f is a continuous real valued function defined on -1 to +1 and integral -1 to +1 f of x to the power of n dx is equal to 0 for all n greater than or equal to 0, then fx is equal to 0 for all x belongs to -1 to +1. this is precisely option 1 implies f of x is equal to 0. By this result, the option 1 implies f of x is equal to 0 for all x belongs to -1 to +1. Thus, the option 1 is true. So option 1 will imply f of x is equal to 0 for all x belongs to -1 to +1. Go to the option 2. Integral -1 to +1 f of x px dx is equal to 0 for all real polynomials p of x. Will it imply fx is equal to 0 for all x belongs to -1 to +1? Yes. Yes, this will imply f of x is equal to 0. And this follows from the option 1 above. Now, integral -1 to +1 f of x px dx is equal to 0 for all real polynomials px. It's given. It's given. This implies integral -1 to +1 f of x into x to the power of n dx is 0 for all n greater than or equal to 0. Why? Why? Because x to the power of n is a polynomial, and integral -1 to +1 f of x px dx is equal to 0 for all real polynomials. So x to the power of n is also a polynomial. Therefore, integral -1 to +1 f of x to the power of n dx is 0. And x to the power of n is a polynomial for all values of n is equal to 0, 1, 2, 3. That is n greater than or equal to 0. Therefore, integral -1 to +1 f of x into x to the power of n into dx is equal to 0 for all n greater than or equal to 0. Agreed. This is precisely, we have come to the option 1. So, this will imply f of x is equal to 0 for all x belongs to the closed end bounded interval -1 to +1 as in option 1. Right. So, thus option 2 implies f of x is equal to 0 for all x belongs to -1 to +1. So far, both the options are true. Both the options are implying fx is equal to 0 for all x belongs to the closed and bounded interval -1 to +1. Let's move to the next slide. Option 3. Integral -1 to +1 f of x into x to the power of n dx is equal to 0 for all n greater than or equal to 0 odd. That is, n is odd, n greater than or equal to 0, n is odd. Will it imply f of x is equal to 0 for all x belongs to the closed interval -1 to +1? This is not so, because of the condition n greater than or equal to 0 is odd. Let us consider f of x is 1 for all x belongs to the closed and bounded interval -1 to +1. Is a constant function, right? Now, then f of x into x to the power of n. F of x is 1 into x to the power of n, x to the power of n. What is n? N is odd. So, x power n is an odd function because n greater than or equal to 0 is odd, is given to us. Now, recall this result from the integral calculus. Integral -a to +a, definite integral f of x dx is equal to 2 times integral 0 to a f of x dx. If f of x is an even function, is equal to 0 if f of x is an odd function. Now, integral -1 to +1 f of x to the power of n dx will be integral -1 to +1 of x to the power of n dx. But x to the power of n is an odd function, therefore it is equal to 0. Is equal to 0. So, integral -1 to +1 f of x into x to the power of n dx is 0. But what is fx? Fx was 1. Does it imply fx is equal to 0? No. For f of x is equal to 1, this integral minus 1 to plus 1 f of x to the power of n dx, when n is odd, is 0. So this does not imply fx is equal to 0. Therefore, option 3 is not true. Option 3 does not imply f of x is equal to 0 for all x belongs to minus 1 to plus 1. Option 4, integral minus 1 to plus 1 f of x to the power of n dx is equal to 0 for all n greater than or equal to 0. Even, will it imply fx is equal to 0 for all x belongs to minus 1 to plus 1? So, this is also not so. Consider f of x is equal to x for all x belongs to minus 1 to plus 1. Now, f of x into x to the power of n will be, f of x is x to the power of n. X into x to the power of n, x to the power of n plus 1. But what is n? N is even. What will be n plus 1? Will be odd. Will be odd. Now, integral minus 1 to plus 1 f of x to the power of n dx is equal to integral minus 1 to plus 1 of x to the power of n plus 1 dx. What is n plus 1? Is an odd. So x to the power of n plus 1 is an odd function. When it is an odd function, its value is 0 as for this, since the integrand is an odd function. Now, is it implying fx is equal to 0 for all x belongs to minus 1 to plus 1? No, fx is x. Therefore, option 4 does not imply fx is equal to 0 for all x belongs to the closed and bounded interval minus 1 to plus 1. Summarizing all the options, the answer to this question is options 1 and 2. That is the detailed discussion of the solution of the problem from real analysis, which is actually an application of Weierstrass Approximation Theorem. So that result, what I have mentioned and used in option 1, I would like to give you a proof for that. So we'll consider that result in the next slide, and I will give elaborately its proof. So the proof of the result. What's the result? If f is a function from minus 1 to plus 1 into r, is a real valued function defined on minus 1 to plus 1, and it is a continuous function, and integral minus 1 to plus 1 f of x to the power of n dx is equal to 0 for all n greater than or equal to 0, then fx is 0 for all x belongs to the closed and bounded interval minus 1 to plus 1. This is the result what we have used. Now proof. We have f is a real valued function defined on the closed bounded interval minus 1 to plus 1, and it is a continuous function. Integral minus 1 to plus 1 f of x to the power of n dx is equal to 0 for n is equal to 0, 1, 2, 3, so on and so forth. So now it's a continuous function defined on the closed and bounded interval minus 1 to plus 1. The closed and bounded interval on R is compact. So that means f is continuous on a compact set, therefore f is bounded. Right? F is bounded. What do we mean by that? There exists capital M greater than 0 such that mod of fx is less than or equal to m. Right? For all x belongs to minus 1 to plus 1. Agreed. Now, since f is continuous on the closed and bounded interval minus 1 to plus 1, by Weierstrass Approximation Theorem, there exists a sequence of polynomials p and x that converges uniformly to fx on the closed and bounded interval minus 1 to plus 1. What the Weierstrass Approximation Theorem says? Every continuous function can be approximated by a sequence of polynomials, and that is by Weierstrass Approximation Theorem. There is a sequence of polynomials p and x that converges uniformly to f of x on minus 1 to plus 1. Let epsilon greater than 0 be given. There exists a natural number n which depends only on epsilon, which you can see, such that n greater than or equal to capital N will imply mod of p n x minus f of x is less than epsilon by m. The sequence of polynomials converging to f of x. And this is true for all x belongs to the minus 1 to plus 1 because of the uniform convergence. Right. Therefore, for n greater than or equal to n, mod of f of x into p n x minus f of x square will be, fx can be taken common. So mod of f of x into p n x minus f of x, that is equal to mod of f of x into mod of p n x minus fx. Mod of fx is less than m because it is bounded, and mod of p n x minus fx is less than epsilon by m because it converges. So this is equal to epsilon, is valid for all x belongs to the closed and bounded interval minus 1 to plus 1, for all n greater than or equal to n, which only depends on epsilon, works for all x belongs to minus 1 to plus 1. Now this tells you fx into p n x, the sequence, converges uniformly to f of x square on minus 1 to plus 1. Yes. We continue in the next slide. We have seen fx into p n x converges uniformly f of x square on minus 1 to plus 1. Therefore, integral minus 1 to plus 1 f of x square dx is equal to integral minus 1 to plus 1 limit n tends to infinity of f of x p n x dx. How? It converges is okay. F of x p n x converges uniformly to f of x square on closed and bounded interval minus 1 to plus 1. Agreed. But how come this integral is coming? Now, f of x is continuous, p n x is continuous, because of polynomial. Fx multiplied by p n x is continuous, therefore is Riemann integrable. And f of x continuous, f of x square is continuous, it's also Riemann integrable. These are Riemann integrable, and f of x p n x converges uniformly to f of x square. Therefore, the integral of minus 1 to plus 1 f of x square dx is equal to integral minus 1 to plus 1 limit n tends to f of x into p n x dx. Yeah, you have to remember this result. And now, because of uniform convergence, the limit will come out of the integral. So this is equal to limit n tends to infinity of integral of minus 1 to plus 1 f of x p n x dx using the uniform convergence. We have integral minus 1 to plus 1 f of x to the power of n dx is equal to 0, and for n is equal to 0, 1, 2, so on and so forth. It is given to us. Now let us take any polynomial. P of x is equal to sigma I is equal to 0 to k ai into x to the power of I, be any real polynomial. Then integral minus 1 to plus 1 f of x px dx is equal to integral minus 1 to plus 1 f of x into sigma I is equal to 0 to k ai xi x to the power of I dx, and that is equal to sigma I is equal to 0 to k ai into integral minus 1 to plus 1 f of x into x to the power of I dx, which is 0 because I takes the values 0, 1, 2, 3, so on and so forth. So here n takes the value 0, 1, 2, 3, then it is 0. It is given. So this is given to us. Therefore, this is equal to 0 for any polynomial. For any polynomial. Therefore, go back to here. Integral minus 1 to plus 1 f of x square dx is equal to limit n tends to infinity of minus 1 to plus 1 of p n x dx. This is 0. What is p n x? Is polynomial. For any polynomial, it is 0. Therefore, the limit of that one is also 0. That means for each p n x, the value is 0. That means it is a sequence of 0, 0. Every term is 0. So the limit will be 0. Now you recall a result. If f greater than or equal to 0, f is continuous on the interval, closed interval a comma b, integral a to b f of x dx is equal to 0, then f of x is 0 for all x belongs to the closed and bounded interval a to b. Now f of x square is positive and f of x is continuous, f of x square is continuous, and f of x square is greater than or equal to 0, and integral minus 1 to plus 1 f of x square dx is 0, then f of x square is equal to 0 for all x belongs to minus 1 to plus 1. In this result, in the place of f of x square put, then this will imply f of x square is equal to 0 for all x belongs to minus 1 to plus 1. This will imply f of x is equal to 0 for all x belongs to minus 1 to plus 1. That's precisely what we wanted to prove, hence the theorem. So that is the result what we have used, and the proof of it, that result is definitely a difficult one, but remember the result, and if you use it, then it becomes easier. That is the detailed discussion of the solution of this problem. I am sure that you have understood the solution of this problem. Thank you for watching my video now. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. We hope to meet you once again in another episode of learning. Enjoy learning mathematics. I wish you all the best. Thank you.